I'm going to talk about bridges and how engineers view them. There's lots of different types of bridges and they all use slightly different engineering principles to overcome slightly different problems. But essentially, a bridge is a structure that spans an obstacle or a void, a gap, and is able to support people or vehicles to cross it. Many bridges today are made from steel or concrete, but lots of other materials have been used in the past. And for example, you wouldn't be wrong to call a tree that's fallen over a river a naturally occurring bridge. When an engineer is building a bridge, there's a lot of things that they might need to know. The length of the bridge would be one. The lay of the land beneath the bridge. For example, could I build a tower halfway along the bridge that could support its weight, or does it need to be able to support itself from end to end? Another question would be about the load that the bridge is required to carry. How heavy will it be? How will it be distributed? And so on. In a minute, I'm going to show you how to use paper to overcome a simple task with a paper bridge. But first, let's have a quick talk about some of the ways that a bridge can fail. One of the ways that a bridge could fail is if it collapses. This could be that the load is centered in such a way that it creates too much stress within the structure of the bridge, and certain components of the bridge will fail. They'll break or they'll stretch over time, or this could happen quite dramatically and quite suddenly, and the bridge will at some point collapse. Another very interesting way that a bridge can fail is something called resonance, which I don't have enough time to talk you through properly now, but essentially the length of a bridge will correlate to a certain frequency. So that could be the number of steps per second of people walking across the bridge, or it could even be a particular wind speed going beneath the bridge. And that can cause solid material such as steel or concrete to wave and bend and act as if they were made of something flexible like rubber. The type of failure that I'm going to show you how to avoid now is called bending, and it's as simple as it sounds. It's when a bridge bends under the load that it's trying to support. I'm going to show you how to get around this using paper. I've got a makeshift space which is made from a candle and the box that my watch came in, and I'm going to use a rudimentary weight just to kind of show you how you might try to deal with bending. This is a piece of paper. It's actually my lecture notes for maths, but I've done the exam, so I don't need that anymore. I'm going to use this across this gap here to try and support this weight. Now, I am doing this from home because of the lockdowns. This is the best weight I could find. It's my old Swiss Army knife, and because it's made of steel, it's quite dense, so this is quite heavy for a simple paper bridge. So let's start off with this piece of paper, folded in half, so it's 2 pieces of paper thick, and let's see what happens if I put the weight on top. So what we've seen there is the paper bending. Why is this? Paper is quite strong. If I pull on it from each end, it's quite resistant to that tensile strength, but it's not very resistant to bending. So how could we go about trying to improve that quality? This time, I've got my sheet of paper, and I've also got another 3 sheets of paper folded in the same way, more of my lecture notes, which I'm going to use to make this 8 pieces of paper thick. So now we're going to put the same weight on top, and let's see what happens here. Once again, the bridge just wasn't strong enough. So at this point, should we assume that paper's just not suitable for supporting this weight for the bridge, or is there something different that we could try? What I'm going to do now is take away these pieces of paper, and I'm going to put in 1 piece of paper. So this is corrugated. So originally, this was 1 piece of paper. I'll show you that now. It's 1 piece of paper, which I've folded in half, just like the others, and then I've folded this pattern into it. So what I've done is I've created a cross section here, which is bent, and the cross section essentially is the shape of this face here, which is then extruded along the length of the beam. So let's pop that down as the bridge. It's even a bit bent out of shape, but let's try and put the weight on there now. This is the point of engineering. We're not trying to throw loads of material at a problem to solve it. We can use our brains, we can apply some principles of physics, we can use a little bit of maths to create something that will perform better than a bigger, heavier bridge. And that's engineering. So next time you see a bridge, have a little look at it. And perhaps you'll notice some features on that bridge, and you'll be able to have a think about why it is the way that it is. I'm going to do this one more time. I'm going to go back to the 4 sheets of paper that I had folded in half earlier on. So let's put them on there. What I'm going to do differently this time is I'm going to apply the load in a different way. I'm going to change the distribution of this load. So instead of putting it this way, which we've seen will cause the paper to bend, I'm going to put it sideways. Now, I'll show you in a second. This gap is wider than the knife. That knife's not supported by either end. What I've done is I've just changed the distribution, and you could see this as, for example, 3 cars that each weigh 1 ton versus a van that weighs 3 tons trying to cross your bridge. I hope that demo has given you a little bit of insight into how engineering allows you to design something to perform better without necessarily just throwing more material at it.